Welcome to the flock. Let's dive into the concept of Avogadro's gas law, equating both volume and moles together by solving problems such as this and this. Stick around to see how it's done. But first, what is Avogadro's law? It's the gas law that assumes that if pressure and temperature are held constant, then we can say that the volume and the number of moles of a gas vary directly. What does it mean to vary directly? Well, in simple layman's terms, it means that if the volume goes up, the moles went up. And if the moles go down, then the volume goes down. This concept is easiest to see by blowing up a balloon. Right now, the volume is very minuscule for this balloon. However, if I add moles of gas to it by blowing into it, the volume of the balloon gets much bigger as I add more moles of gas. So more moles, bigger volume. Less moles, less volume. We symbolize this direct relationship by saying volume is proportional to moles, and moles is represented by an N in all gas law equations. The actual mathematical relationship we're going to use is initial volume divided by initial moles is set equal to our final volume divided by the total amount of moles that we have. Keep in mind that this is a total value. So if a question asks you how much was produced or how much was lost, you're probably going to need to subtract out or add in the N1 value that you started with, because that's included in your total N2. So back to this baking bread problem thing. If you've never made bread in your whole life, you should know that in order for bread to rise, you need to add yeast. And we add yeast because the yeast itself is going to break down the carbohydrates, the sugar that's inside the bread dough. And when it breaks it down, it creates a byproduct of carbon dioxide gas. And carbon dioxide gas is really good at making bubbles inside the dough, causing it to therefore rise. So if we're assuming then when the bread dough is first combined that there's roughly 0.5 moles of CO2 gas, that would be our N1 to start, in 2 liters of dough, that would be our V1, initial volume. And after baking the bread, we see that the bread rises to a total new volume of 4.95 liters, that's our V2. How many moles of CO2 gas were produced? That would be our N2 that we're solving for. Now keep in mind here, it's asking how much was produced. So we're going to have to subtract out our initial N1 to figure out how much was produced. Now all we have to do is plug and chug into Avogadro's law mathematical setup. Our V1 is the 2 liters divided by our N1, which was the 0.5 moles. We're going to set that equal to our 4.95 liters, which was our final volume, over X, that's our N2 that we're solving for. I'm going to start this by dividing my 2 by 0.5, and that gives me a value of 4. And that 4 is still equal to 4.95 liters over X. Now to get the X out of the denominator, there's a few different ways you can do it, but I prefer doing it this way. I like to multiply both sides by the X, just like we were if there was a value on the bottom and the X is on top. This will get rid of the X out of the denominator on the right side, and then we end up with the format that looks more familiar. We end up with 4x is equal to 4.95. I think most people know how to solve that setup versus the other way. So in my mind, it's a little less intimidating. Now, in order to undo the 4 from the x, which is currently multiplying, we need to divide. So divide off your 4 from both sides, and that will get x alone. 4.95 divided by 4 gives us a value of 1.2375 moles as our N2 answer. Now remember, the question is asking how many moles of CO2 were produced. This is the total amount of moles that was produced. We already started with 0.5 moles, so we need to subtract out the 0.5 in order to figure out how much was produced. Once we've subtracted out the 0.5 that we started with, we end up with 0.7375 moles of CO2 gas was produced during the reaction. Remember that Avogadro's law can only hold true if the pressure and temperature are constant. Now that you've seen me try one of the calculations, go ahead and pause the video here and give this one a shot on your own. Ready? Go! Let's check your math. Now before we do any math here, recognize that the semantics of this word problem are a little different. It's saying that 1.9 moles of carbon dioxide gas escaped. That means we still need to figure out how much is left inside the balloon after the 1.9 moles escaped. So our N2 value is not this 1.9 moles. Our N2 has to be 3.5, what we started with, minus our 1.9, what got leaked out of the balloon. So what we have left in the balloon is 1.6 moles of gas, and that is the value we use for N2. We know that the moles went down, and since Avogadro's law is a direct relationship, if the moles go down, the volume should also go down. So before you ever calculate, make sure you understand conceptually what your value should end up looking like, so that if you do a calculation incorrectly, you'll be able to pick it out rather easily. So for example, we should know that our V2, if calculated correctly, should be less than our V1 of 25.5 liters. So you should have found a value of 11.65 liters as your new V2. 11.65 is in fact less than 25.5, so we know we did our math correct in that the moles went down and so did the volume. Flashback to STP, standard temperature and pressure. If we take a look at these three balloons, helium, nitrogen, and methane, we see that they are each held at standard temperature, 0 degrees Celsius or 273 Kelvin, and standard pressure, 1 atm. Since each of these balloons contains exactly 6.02 times 10 to the 23rd molecules of gas, which is, of course, Avogadro's number, and representing a mole, we know that each of these contains 1 mole of gas, and 1 mole at STP, standard temperature and pressure, is equivalent to a volume of 22.4 liters. This is an important conversion factor because you can use 22.4 liters over 1 mole, or 1 mole over 22.4 liters to convert from liters to moles or vice versa. And since we are dealing with moles now, after all, thanks to Avogadro's gas law, keep in mind that you might just need to use that 22.4 liters is equal to 1 mole to solve for one or the other. Here's that other question I showed you at the beginning of the video. If we say that young adult males between the ages of 18 to 25 can expand their lung capacity from 0.5 liters to a maximum of 6 liters of oxygen, how many grams of oxygen could be contained in male lungs at maximum capacity if we assume that the resting state contains 10 grams of oxygen? Notice here that we're given 0.5 liters as a V1 and we're given 6 liters as a V2. We're trying to solve for grams? What? We don't have a gas law with grams in it. You're right, we don't. But we do know that we can convert grams to moles using molar mass. You will never escape the stoichiometry, ever. So before we can do anything with the gas law, we need to first convert our 10 grams of oxygen to moles. Now that we know the moles that are at resting state, now we can plug it into Avogadro's setup. We're going to have our 0.5 liters over 0.3125 moles. Set that equal to 6 liters over X. Now we just have to plug and chug into our calculator. 0.5 divided by 0.3125 gives us a value of 1.6. That's still set equal to 6 over X. In order to get X out of the denominator, I'm going to multiply it by both sides. And now, of course, to get X alone, I need to divide off the 1.6 from both sides. And now we can clearly see that X is equal to 3.75 moles. So at max capacity, a young male can hold 3.75 moles of oxygen in their lungs. However, let's go back and make sure we actually answered the question. It's asking for grams. Well, looks like we need another magical line to freedom. And there you have it, folks. At max capacity, a young male can hold 120 grams of oxygen in their lungs. Now it's your turn. Go ahead and pause the video here and see if you can solve this gas law problem all on your own. Ready, go. hopefully you got a value of 5.54 liters as your final answer. It would make sense that if we added moles to the balloon that already contained 2.51 moles, that our volume would have to be bigger than what we started with. Since we started with 5.29 and we ended up with 5.54, we know we must have done this right. Before you move on to the next lesson, make sure you test yourself before you wreck yourself. Make sure you can answer these questions about Avogadro's law. In this lesson, we discussed how Avogadro's law relates both volume and moles together in a direct relationship. If moles go up, the volume goes up. If moles go down, the volumes go down as well. We also reviewed standard temperature and pressure. We know that 22.4 liters equals 1 mole of gas for any gas at standard temperature and pressure, which is 1 atm and 0 degrees Celsius or 273 Kelvin. You can use this information as a conversion factor to convert between volume and moles. We also practiced some problems using gas stoichiometry and molar mass. Blast from the past, you'll never escape the molar mass. Please give this video a quacks up, and I hope your day is just ducky. Subscribe to the Duck. Quack you later.
No ducks, no glory.